So here we're gonna do example of converting basically an instruction or assembly instruction to machine code. So I have chose 3 different instructions that are all R format, and they are like the pattern of those can be found in this table. So the first thing is that, so let's look at this add unsigned. So we have the 3 register 20, 16, and 5. And if you look at this table, we can see that this add u is here. So I'm just going to copy that to have this for reference. So we said that we are going to follow this pattern, and we had, so if I copy also this one just to have as a reference. So this is the pattern that we have for the R instruction. So basically the first step before converting is to understand what is this instruction that you're converting. So because if you remember from beginning of the chapter, we had 3 different, we had like R format, we had I format, and we have J format. So we have different kind of like different formats for these instructions. So the first thing is that you see this instruction and you say, okay, is this an R format or is it the I format? So we're gonna see that later, but for now, you know that all the R formats are having these 3 registers here. And after that, you look up the table and you can see that this is the pattern for this instruction. So then you have to start basically write each part of the instruction to get to the final instruction, the 32-bit that we're gonna have, that the processor like would understand. So the opcode for this one, or the operation code, is going to be basically the 6. So we know that we have zeros. So this is gonna be the opcode. And then the last part, so this part, which is 11, right? So 8 and 3, so 11. So this 11 bits here are the extended operation code. So then we can put that here. So 1, 2, and then 0, 0, 1, 0, 0, 0, 0, 1. So that is the extended code. So the 3 registers here, we said there is 5 each. So first we have the S, and that's going to be 5. So we have to look at this here to know the order. So this S 5 bits is not the first one. You have to look at the order. So you see that here is the basically the second one, and that is register 16. So this register 16 is supposed to be here. So how do I convert 16? So that goes back to the binaries. We basically divide by 2 and all that, but 16, it's 2 to the power of 4. So that means if it's 0, 0, 0, so that's 0, 1, 2, 3, 4. 0 and then 1. So that should be 16. And we have 5 bits only here. So 0, 1, 2, 3, 4. So indexing from 0. So that's total of 5 bits. And this is gonna be 2 to the power of 4. That is 16. So here, the next one is RT. And we see that here is we have another 5 bits. And this one is going to be the last register here. So you just have to look at the pattern. So the last register that here we have is 5. So how do I write 5 in binary? You basically have to convert that again. So I know that it's going to be 4 is going to be 0, 1, 0, and then there's 1, and then it's going to be 5 bits. So this is 0 to the power of 1, 0, 1, 2. So that's 4, and then plus 1, 5. So this is going to be 5. And then we have RD. For RD, we again look at this one and we see that this is the next 5 bits. And here is appearing the first. So if you look at that, then look at back in your original instruction, that's register 20. So we have register 20. So I can see that 20 is 16 plus 4. So that's 0, 1, 2, 3, 4. So that's 16. And then 4 is going to be 0, 1, 2. So this one is going to be a 1. So that is going to be 20. And there you have it. So this is going to be your final, basically, register. So sorry, final instruction. So if you have basically 32 bits on your memory, so when the assembly is done, so you have some memory address, and then you have some content. So this 32 bits literally is going to be written in that that place, and the next instruction is going to be on the next one, and so on. So that's an example of basically of the R format. Then now we're gonna look at the next example. So this is the second example that we have, and I'm going to follow the same thing. So first you identify that this is the R format. And so let's look at the table that we have, and that was a mult. So we know that's a multiplication. I'm just gonna copy this here for reference. And then let's take the table also, same as this one. So these are all R format. Okay. So the process is exactly the same. So again, the first thing, so let's say you identify that's the R format, you find it from the table. So this is the pattern that you have to follow. And again, here we set that 6. These are 5 each, 5 bits. And then the last one, so this is the extended opcode, and that was 11. So if you add all of these, that's 6 plus 15. Well, 6 plus 15 plus 11, that is going to be 2 here and 1, 32. So that's basically the 32-bit our instructions. Okay, so let's start. So the first thing is, again, the opcode is for R is all 0. You don't need to memorize that. You can just, again, look at the table. So here we have the 6 zeros, 4, 5, 6. The last 11, so here is 4, 8, and 9, 10, 11. So till here. So that's till here, basically. So that's going to be the 11-bit for the extended opcode. So 3 zeros, and then 0001, and then 1001. Okay, and then you see here that these ones are hard coded to 0. So the next 5. So in the previous case, this was actually a register. And that was our destination. If you remember, that was a D. So that would be the first thing that we had here. But here it's hard coded to 0 because we only have 2 registers. And that's fine because we are not storing the basically the answer there. We are storing it in the registers itself, in the high and low registers itself. So here 3, 4, 5. And then starting from here, we have the S. So the S is going to be the first one here. So it's number 12. And then the next one is T. So that's gonna be number 16. So what I have to do is now to convert this 12 and 16 to binary. So 12, I know it's 8 plus 4, but then you don't need to do that. You can do the same method that we had. So 12 divided by 2 is 6, remainder 0. 6 divided by 2 is 3, remainder 0. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, and remainder 1. So it's going to be 12 is going to be 1, 1, 0, 0. And we have 5 bits, so I have to pad with 0. And if you look at that, it's going to be 0 to the power of 2 to the power of 0, 1, 2, 3. So that's 8. And this is to the power of 2. And that is going to be 4. So 8 plus 4 is 12. So that's just kind of like a reminder from the previous chapters. So here we have 16. So 16 we've seen before, it's going to be only 1 bit, which is to the power of 4. So 0, 1, 2, 3, 4. So that's 1, 0, 0, 0, 0. And that's basically 16. So that's your instruction. And if you follow just these steps, you would be fine to basically converting this. One more thing I want to add is that these instructions usually are represented in hex. So if you look at the memory, so if you ever see that basically your machine code is in hex, you shouldn't be surprised. That's basically the same thing that is converted. So if you want to convert to this one to hex, basically, you're going to divide them every 4, or you're going to group them every 4. So this 2, and then 3 here and 1 there. So this is going to be 0, so 0x. It's going to be, for example, this 4 going to be 0. This is going to be 0, 0, 0, 1. So that's going to be 1. This is going to be, so you have to convert that. 1, 0, 0, 1. It's going to be basically 0 to the power of 0, 1, 2, 3. So that's 9. So something like that. And then the next 4 is going to be 0. So basically you continue that. And the next 4 is 0, 1, and then 3, that's going to be 0 again. This 4 is going to be 1. And then 1, 0, 0, 9. 1, if we are correct here, it's going to be 9. So basically your final number is going to be x 0, 1, 9, 0, 0, 0, 1, 9. So that's the same representation, or the same value, but the different representation of this binary number. And these are all, or both of them, are basically this instruction that is assembled. So again, the processor can understand this. Okay, so now let's move to the next and last example. Okay, so here we have another instruction again, and let's do the same thing. So it's moved from low. So this one is, again, is R format, but I put it on purpose here because it's only one register. So that's a bit, again, different, because typically your R formats are always like that. So you have 3 registers. So let's look at move from low. So you just find it on the table. So that's the pattern that it has. So let's keep that. And let's keep this just as a reference. Okay, so this is actually very simple because you have one register, so you have a lot of zeros. So if you look at this one, we had 6. So this is 4, 5, 6. So that's the opcode. And then we have here 5. 1, 2, and this 3 here. So that's 5. That is the RS. That is the opcode. And then you have another 5. That is the RT. And then this 5 is a D. And then the rest of it is that extended function. So you see that we have here one register only. And here we have a lot of zeros for this RS and RT. So these are all zeros. So it's basically those registers are missing and we don't need that. And that's okay. It's still, there is the R format, it's a valid R format because the pattern is there. So if you want to convert this one, basically it's gonna be 6 zeros here. The RS is going to be 5 zeros. The RT is going to be again 5 zeros. We don't have any register here that would be RS or RT. So here 5 zeros, 4, 5. And you see this one register here. That's RD, and that is basically these Ds here. So that is the 24. So we have register 24. And 24 is, I cannot remember like the exact number, so let's do that. So 24 divided by 2 is equal to 12, remainder 0. And then 12 divided by 2 is equal to 6, remainder 0. 6 divided by 2 is equal to 3, remainder 0. 3 divided by 2 is equal to 1, remainder 1. 1 divided by 2 is equal to 0, remainder 1. So this is going to be our number. We can write it from this side. And that's R. So 1, 1, 0, 0, 0. So that's actually 16 plus 8, which is that 16 plus 8? Yeah, it's gonna be 24. So that's right. And then the opcode or the extended opcode, that's 11 bits. It's going to be this pattern, and that's just every operation has a unique pattern. There is nothing much to it. 2, 3, 3, 2, 3, 1, 0, 0, 1, 0. So basically, that's your assembled version of this operation. And again, that's the basic steps. You just have to find the right pattern and convert each part of it.